So now in this video, we're going to look at the NOT logic gate. That's the symbol, but usually there's no A or Y there, and that might be X, and so on. But any case, we have a triangle. That basically means a buffer. What you put in, you put out, but then there's a little dot there, which is the inversion dot, which means it gets flipped around. So if you give a high input, you're going to get a low output, and if you give a low input, you're going to get a high output. And so right now we have a high input. I'm to the positive supply. You can see the blue LED is connected to the positive supply up there. So the only way it lights up is if the output is connected to ground, as good as it can get, which we have right there. Now I'm going to turn the trim pot towards the negative supply. We get about halfway, and this is not a Schmitt trigger version integrated circuit right here. This is the 7404 right there. And we have both LEDs on at the same time right there. I don't know if they're oscillating or what the deal is, but in any case, now we have just the red one. If we had a Schmitt trigger version, there's usually a little symbol in there, then one would turn off instantly when the other one turns on. There would never be a time where they're both kind of on, unless for some reason a signal was oscillating high and low enough rapidly to get them to flicker. But here we have a steady input, and they're both on. But in any case, we're going to go low there. So there you can see negative supply, but there's negative supply over on that end of the LED right there, negative. And so obviously we don't have a low input coming to the low output there. It's the positive supply, as good as it can provide, going through there, through the LED. So hopefully that makes sense. We have the opposite output of the input. So again, it's like a buffer. The voltage you come in is out, but then there's an inversion where it flips. So that if you give a high input, 5 volts, actually above about half of the supply voltage in this case, then you'll get a low output, which is as close to ground as the output can provide right there. Whereas if you give a low input, somewhere below half of the supply voltage, in this case we're using 5 volts. I don't know what voltage range you can go with this integrated circuit. It might be made for about 5 volts, but in case we get a low input, we get below about half the supply voltage, below 2.5 volts, we'll get a high output, as high as the output can go. Again, that's stuff we can measure and also check the data sheet to make sure. So yeah, that's the basic schematic symbol. I added some info there, that A and the Y. If they put a part number there, that will help out a lot. Now, this is a high-speed CMOS version of this integrated circuit. I'm going to get the kit, and also you're going to notice I'm missing some there. I actually have 2 of these kits, and I should not be touching these right there. They can be damaged with static discharged really easy. So that's probably why I'm short. Again, I have a second kit, and so I try to keep that one full. If I fry one from that one, I'll take it out of this one and put it back. But yeah, this is the high-speed CMOS version right there. And before I handle them, I try to touch the negative supply right there. And yeah, if you wire this up, it all looks right, but you're not getting any power out, you may have fried it. So I want to mention that. But yeah, this is an integrated circuit. It's a HEX NOT gate. That means there's 6 NOT gates. They are not Schmitt trigger though. It's important that you pay attention to that. The 7414 is a Schmitt trigger version of this. You won't see the LEDs both on unless they happen to be rapidly flipping back and forth enough that they both look on, but in that case the signal is bouncing back and forth rapidly as well. There will never be a point with a steady input voltage where both of the LEDs are on, unless something really went wrong. But in any case, we have just a NOT gate without the Schmitt trigger. So there is a middle ground region here, whereas the Schmitt trigger, it changes slightly where the high and the low points are to make sure the output is locked into either high or low until you change the voltage enough in the other direction. So there's other versions that are not high-speed CMOS, but these are the main ones right now, HC. So you'll probably see this, but if you look at old schematics, you might see a 74 and then something else, maybe just H or maybe just C, 04. There's all kinds of them. So yeah, we got the trim piles as a voltage divider. So another thing with these integrated circuits, so a lot of the op amp circuits I just leave the one I'm not using, because there's a lot of op amps with 2 or even 4 on the integrated circuit. But usually I'm fine with my demonstration circuit just leaving the other circuitry, the inputs for the other circuitry, floating just in the air with nothing connected to it. Here you see I got a bunch of jumpers, so negative supply, positive supply there, just because I only have so many gray ones. But yeah, you can go either positive or negative supply. Always check the data sheet though for their best recommendations. But we have to power the integrated circuit. It may only work with 5, again check the data sheet, but usually 5 is good for these. So all the inputs there, I'm tying to a supply voltage. That locks the output voltage in place. A lot of times I think there's internal oscillations or something, and when you cut the power to the load, then like you'll still see like a fair amount of current flowing. You know something's wrong because there should not be current flowing. And another thing, when I get this about halfway and they are both like lit up, you can see we got a higher current there. So that's an indication that both LEDs are actually on. They're not oscillating back and forth right there. And there may be like other problems. So again, this is kind of intended more for a solid high input jumping to a solid low input. It's not really good for these middle ground voltages, right in the middle ground. But you know, it's probably not damaging anything. Maybe you like that effect too, you know, who knows. But in any case, that's what we got. We got the inputs tied to a voltage to help lock the outputs in place. And again, I'm going to touch that before I touch the integrated circuit. But yeah, let's pop these out and see how they do. So yeah, this went on long enough, so I'll just quick do this demonstration and see if the floating inputs cause a problem. Yeah, look at all that current flowing. I yanked this. We should not have any current flowing right now. So yeah, those floating inputs are causing a problem. But in any case, this went on pretty long, but hopefully you still enjoyed these integrated circuits. As I said, you know, they're kind of finicky. There's some rules you got to learn about them. You know, not complex. You know, make sure and tie a voltage to the inputs. You could use like a resistor instead of the jumpers or whatnot. But you want to make sure they have like a solid voltage so they're not oscillating or doing whatever. Also, they're susceptible to shock. So I touched the negative power supply. Other people wear a wristband where they actually ground their bodies and whatnot. There's other precautions, but as a hobbyist, for the most part, like you can handle these. You're gonna fry some though, just from touching them. But this discharging seems to help me. I don't think I've damaged one since I made sure to discharge myself first. But in any case, that's it. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.